we're going to start the PowerPoint on momentum. So momentum is inertia in motion. So if I had to describe momentum in my own words, I would say it's basically how hard it is to stop something that's in motion. So linear momentum of an object equals the product, which means mass times velocity. Moving objects have momentum. So in order for something to have momentum, it has to be in motion. And it's going to be a vector quantity, so that means it has to have a direction, remember. So the momentum equation, it's proportional to the mass and velocity, so it means it's going to look like this. Now, momentum is a little funny. Although it starts with an M, it's going to be represented by a P, and that's because our M was taken, right, by mass. Our units for momentum are going to be kilograms times mass per second, and that's because momentum is mass times velocity, and mass is measured in kilograms and velocity is measured in meters per second. So when we talk about momentum, we're also going to talk about collisions. So in collisions, you're going to have two or more objects that exert forces on each other for a brief instant of time. And these forces are significantly greater than any other forces that they may experience during a collision. So we're going to do a sample problem about a taxi cab. So what is a taxi cab's momentum that has a mass of 0.14 kilograms moving at a speed of 1.2 meters per second? So our mass is 1.4 kilograms. Got to be careful on those, you guys. It will mess you up. Our velocity is 1.2 meters per second, and we're looking for the momentum. And remember, momentum is P, not M, like I just said. So momentum, the equation is mass per times velocity, and this is on your pink sheet. Plugging in, we have 0.14 times 1.2. And our answer then will be, multiply those two numbers together, 0.17 kilograms times meters per second squared. And I just want to mention this, you guys, so it has direction. So your taxi is going to the left here in the picture. The velocity is 1.2 meters per second, and our momentum is 0.17 kilograms times meters per second. Okay, so we need to talk about one more thing, and that's conservation of momentum. So conservation of momentum is just that. The total momentum of an isolated system is constant. It remains the same. So this is with no external force acting on the system, of course. And the momentum before is the same as the momentum after. So remember, the equation for momentum is P equals M times V. So that means the momentum before collision is going to be the same as the momentum after. So that means all the momentums of all the different parts of initial reaction or collision is going to be the same as all the different ones final. And then one more thing. So if we're talking about specific objects, you can take a specific object initially, or situation 1, and apply that, and that's going to be equals to situation 2. And I'll show you how that works out, okay? Okay, so law of conservation of momentum can be derived from Newton's second and third laws. Okay, so second law, remember, was F equals ma, and then the third law is forces are equal but opposite. Okay, so we're going to do one more example problem here. So an astronaut of mass of 80 kilograms pushes away from outer space station by throwing a 0.75 kilogram wrench, which moves with a velocity of 24 meters per second relative to the original frame of the astronaut. What is the astronaut's recoil speed? So the mass of the astronaut is 80 kilograms. The mass of the wrench is 0.75 kilograms. And the final velocity of the astronaut is what we're looking for. And the final velocity of the wrench is 24 meters per second. So we're going to use that equation I just showed you. So Your mass of your astronaut times the velocity of your astronaut is going to equal the mass of your wrench times the velocity of your wrench. So the mass of circumstance 1 is going to, or the momentum of circumstance 1 is going to equal the momentum of circumstance 2 because of the law of conservation of momentum. So 80 times your acceleration of the astronaut is going to equal 0.75 times 24. So we're going to multiply and divide there. So your astronaut is going to go 0.225 meters per second squared.